and welcome back, everybody. In today's latest installment of Lonely Guy in a Basement Talks About Mathematics, we're going to talk about relations. And we're not talking about the kind of relations that got Bill Clinton in trouble back in the 90s. No, we are going to talk about the wholesome, good, mathematical kind of relations. So, the word relations very well chosen here because the idea behind what we're going to talk about with a mathematical relation is it's a device based on sets. Everything's going to be based on sets, but it's a device based on sets that keeps track of relationships between mathematical objects. So the idea is that you have one set, let's say set A, and you have a second set, set B, and we want to relate the objects in those two sets. And we have some sort of way of expressing in words, or maybe with equations or some sort of propositional function, what the relationship will be. So on the first line of this table here, I've got set A is the set of all people, and set B is the set of all people. So the two sets that are involved could be the same set, like it is in this case. And in this particular example, an element in the first set of all people is a sibling of an element of the second set, which is also the set of all people. So we're literally talking about familial relations here. When we go to write down a formal definition for what a relation is, order is going to matter. Now, in this particular example, order doesn't matter so much because if you would say x is a sibling of y, it's also true that y is a sibling of x, right? So you can interchange x and y here and it doesn't change the meaning of the expression. However, if I change this to, instead of sibling, if I said father, then you would see that order matters a lot, right? If I say x is the father of y, that's not the same as y is the father of x. In the second example I have here, the two sets are both the sets of integers. So set A and set B are both the set of integers. And we can say one element in the first set, little a, divides an element of the second set is our relationship. That's what we're going to, when we want to say these two elements are related to one another, that's the relationship I'm describing. A divides B, which we have this symbol for A bar B there. Again, this is one of those relations where order matters. If you say A divides B, it doesn't necessarily mean the same thing as B divides A, right? In fact, one can be true and the other cannot be true. 2 divides 4, but 4 does not divide 2. The third example here, the sets can be the real numbers and the relationship can be less than. X is less than y is one way we could relate two real numbers. It doesn't always have to be that the two sets A and B are the same sets. In the fourth example here, the first set is the real plane, which we can think of as a set of vectors, two-dimensional vectors. And the set B is a set of non-negative real numbers. And then the relationship between the two kinds of objects is magnitude. So we could say the magnitude of the vector is this real number. So we're relating vectors to real numbers here by assigning to each vector the length of the vector is a number we can associate it with in a relation. So hopefully you get the gist of it. So then if we think back into what we've been doing recently that keeps track of order, well, you may remember we came up with the concept based on sets of the ordered pair. And that's exactly how we're going to keep track of things in relations. We'll use ordered pairs. So here, without further ado, is the definition for a relation. A relation from set A to set B is simply a subset of A cross B. That's it. There's hardly any structure at all required for something to qualify as a relation. The only structure really is that you need to have a collection of ordered pairs where the first components of the ordered pairs are coming from some fixed set A, and the second components of those ordered pairs are coming from some fixed set B. So that simply describes a subset of A cross B. Now, whenever the two sets A and B are the same, let's say they're both of the sets involved in the relation are both, called A, then we just say R is a relation on A rather than saying from A to A. You could say R is a relation from A to A, but whenever that happens, we usually just shorten that up to say R is a relation on A. So let's start off with a toy example. In this example, we've got the set A is the set of integers 1 through 5, and the set B is the set of letters A, B, and C. Let's focus on R1 here for a second. When you look at R1, you notice that all those first components, 3, 4, 1, 1, are coming from the set A. And all the second components are coming from the set B. So what we're looking at here is a subset of A cross B. So this means R1 is a relation from A to B. For R2, you see that the components, both the first component and the second component of these ordered pairs, are both coming from the set A, because they're all integers between 1 and 5, right? So what we have here with R2 is a relation on A, because it's a subset of A cross A. And likewise, with R3, you notice that all of the components are letters from A, B, and C. And so what we're looking at here is a subset of B cross B, so this is a relation on B. So R3 is a relation on B, i.e. a subset of B cross B. So you'll notice in this toy example, there's no real, like, I don't know, formulaic relationship between the components of the ordered pair. It's just some random nonsense that I made up. But that's all it takes to qualify as a relation. You just have to be a collection of ordered pairs where the first components come from a specific set and the second components come from a specific set. We often come up with these sort of bubble diagrams for relations. For example, if I wanted to depict R1, so let me get R1 in the frame here. So R1 is the one at the top there, 3B, 4C, 1B, 1C. So I could depict that with a bubble diagram by putting all of the elements of the first set A in the left bubble and all of the elements in the second set B in the right bubble, and then just draw arrows from the elements that are paired up. We see that 3B, the ordered pair 3B, is in the relation R1, so I can draw an arrow from 3 to B. And again, order matters. The arrow points at the second component and starts from the first component. 4C, so you have this arrow corresponds to that ordered pair, 4C. Then 1B corresponds to that ordered pair. And 1C would be represented by the arrow from 1 drawn down to C. These kind of diagrams are useful when we're thinking about relations in the abstract. When we're trying to think about general properties of relations, having sort of having a picture to point at. For me, I'm a very visual learner, and so having Venn diagrams and these kind of diagrams really help me conceptualize things. Like, for example, I noticed that there are 2 arrows emanating from the point 1 in the set A. That tells me something about this relation that a little later we're going to find is important. It tells me that this relation here is not an example of what's called a function. Getting past the toy examples where we're just listing some random ordered pairs, the way we typically describe a relation is we use our set builder notation and do something like what I have here. We describe a relation R as, well, we've got some ordered pairs and we say what cross product those ordered pairs live in, and then we give some relationship between the components of those ordered pairs that ties them together. So for example, look at this relation that I have here. L is the set of ordered pairs x comma y in R cross R, so that just means that x and y are both real numbers. And the relationship between the components x and y is here, x minus y equals 2. If only there were some way to visualize the collection of ordered pairs that satisfy that equation. Have we ever seen anything like that? Well, of course we have. If we just graph that equation, we'll have a graphical representation of that relation. Let's do that. That's the same as y equals x minus 2. So I can see the y-intercept is -2 and the slope is 1. So that makes it pretty easy to graph. So all the points on this line here are elements of this relation. So for example, this point here, 2 comma 0. That's an element of the relation L. This point down here, 0 comma negative 2 is an element of L. Indeed, every point that's on that line satisfies that equation that defines the relation, and so all the points that comprise that line is the relation. Here's another example of that sort. C, and we're defining it on R, and that just means the ordered pair, the elements, the components of the ordered pairs are both coming from R. So C is the set of ordered pairs in R cross R, and the relationship between X and Y is this captured by this equation, x squared plus y squared equals 1. Well, surely you recognize that equation as your old friend, the unit circle. So again, any point that happens to lie on that unit circle is an element of the relation. So elements of a relation are ordered pairs. So, for example, you should know lots of points on a unit circle. For example, well, there's that point like 1, 0 and 0, 1. So the points where the circle intersects the axes. But there's also those points like out here at 60 degrees, like 1/2 comma square root of 3 over 2 would be a point that's on that circle. So that ordered pair is in that relation. Likewise, 1 comma 0 is in that relation. So, and then of course there's an infinitude of points that fall on that circle. So this relation consists of an infinite number of points. All right, so yeah, so that's typically the way that relations get defined, by some sort of real mathematical relationship. Could be an equation, could be some other relationship like less than or divides or something to do with modular congruence. We have all kinds of things we can use. Here's another example. In this example, A is the set of integers 1 through 4, B is the set of even integers from -2 up to 6. And then we define the relation R from A to B. Now this time A and B are different sets, and the relationship is A comma B is in the relation if A divides B. So let's write out what the ordered pairs actually are in this relation. Okay, so the first components of these ordered pairs have to lie in A. So what ordered pairs can have 1 as their first component? Well, 1 can be a first component if 1 divides something in the second set, B. So does 1 divide -2? Well, yeah. In fact, 1 divides every integer. You get 1, -2. Because 1 divides -2, you get 1 comma 0. You get 1 comma 2. You get 1 comma 4, and you get 1 comma 6. Okay, then you can think about 2 being a first component. What does 2 divide in B? Well, 2 divides -2, so 2 -2 is in the relation. 2 does divide 0. Remember, things can divide into 0, you just can't divide by 0. So 2 divides 0 because you can express 0 as 2 times an integer. In particular, 0 is equal to 2 times 0. So that's why you can say 2 divides 0. 2 divides 2, so you get 2 comma 2. You also get 2 comma 4 and 2 comma 6. So 2 comma 6 here. How about 3 as a first component? Does 3 divide anything in the second set B? Well, yeah, 3 divides 0. And 3 divides 6. So 3 comma 6 is an ordered pair. But notice that we don't get 3 comma -2. 3 doesn't divide -2, so 3 comma -2 is not in this relation. And then 4, the only thing that's in the set B that 4 would divide is 4 itself. So 4 comma 4. And that's it. Those are all the ordered pairs in your relation. So we have some notation. If R is the name of your relation and you have an ordered pair A comma B in your relation, another way that we can write that notationally is to write A R B. And of course, if A comma B is not in the relation, we're going to use a slash through the R to indicate that A and B are not related. We'd write this as A R, put a slash through that R, B. So we'd read this as A is related to B in the first instance, and in the second instance we'd say A is not related to B. Okay, so let's consider this example at the bottom of this slide. So our relation that we've got is less than or equal on the set of real numbers. Certainly less than or equal, that symbol less than or equal, relates real numbers. It just seems intuitively clear, but how would we think of that in terms of the structure that we have for how we define relations? So our relations are defined as sets of ordered pairs that form a subset of a cross product. So if less than or equal is being defined on the real numbers, I need to think of less than or equal as a subcollection of R cross R. So in particular, like a formal definition of what the relation less than or equal is, it would be the set of all x comma y in R cross R having the property that x is less than or equal to y. Isn't that weird? The symbol that you have used for so long in your life, you're now thinking of it in this completely new way as a set of ordered pairs. So whenever you make the statement x less than or equal to y, another way to say that according to our notation that we have up here. So see, this is the notation x less than or equal to y is like the right hand side up here where you have the R in the middle. So that would be the same as saying x comma y is an element of less than or equal. Both of these things are interchangeable. It's certainly true that 99% of the time we would use the common notation x less than or equal to y like that. But there are instances where when you're proving things in the abstract that thinking about things in terms of ordered pairs is easier to conceptualize. And so sometimes we switch over and use the ordered pair notation when we're talking about a relation. Just depends on the situation and what we're trying to do. I would say more than half the time when we're proving things about relations, we switch to ordered pairs. It just makes it easier to talk about them. But not always. But the point is we need to be able to use the notation interchangeably, okay? Be aware of the two different ways to, indicate one element is related to another. Okay, the next concept we want to talk about having to do with relations is the domain and range of a relation. I'm sure you've seen these words before from back when you had previous classes where you're talking about functions, and when you're thinking about functions, the domain is sort of like the allowable inputs to the function, and the range is sort of like the outputs that you get from the function. But when we think about it in terms of a relation, it's a little different, but it ends up being, of course, it's going to play that same role as it did in previous courses, but it's a little bit more general now. So if we have, the setup is, we have a relation from A to B called R, and then the domain of R, which we're going to use this notation DOM of R, is this set. So I kind of like to think of it in the second form here. The domain of R is the set of all elements in the first set A for which there exists some B in the second set, big B, that pairs with A. So when you say an element little a is in the domain, it means it's the first component of an ordered pair that exists in the relation. This is an easier way to think about it. The domain of R is just the set of first components of ordered pairs that are in R. And similarly, the range, which has this notation here, RAN of R, is this set. It's the set of all B's and big B for which there exists an A in the set big A, where A comma B is in the relation. So B here is the second components, right? So all we're talking about with the range is it's the set of all second components. When you think about it that way, it's super easy in these toy examples to figure out what your domain and range are. Okay, so in this first example that we have here, for R1, what's the domain? Well, the domain's just the set of all first components that appear in ordered pairs. So the domain of R1, just read off the first components. I see 3, 4, and 1. Now notice 1 is listed twice, but since the domain is just a set, we don't list redundant elements. So 1, 3, and 4 would be your domain. Doesn't really matter what order you write the elements in. I happen to put them in numerical order there, but you could have written 3, 4, 1 if you wanted to. It doesn't matter. For the second relation there, R2, its domain Well, just again, read off all the first components that you see. And I see 1, 2, and 3. And for the third example, the domain of R3, the set of all first components there, I see A, B, and C. And now let's go do the range. The range is just as easy. It just means read off what the second components of the ordered pairs are. So the range for R1, so the collection of second components, I see C and B are the only elements that appear as second components. For the second example, the range, so the range of R2, I see 1, 3, and 5 appearing as second components. And for the third example, the range of R3, I see A, B, and C. All right, so easy peasy, right? Whenever your relation is defined in terms of some sort of equation or something along those lines, something a bit more mathy, and you can't just sort of lay out all the ordered pairs and look at them and just read off what the first and second components are, then it gets a little trickier. You have to think about things a little deeper. So let's look at this example here. I'm defining the relation P on R, so that means it's a subset of R cross R, by saying that the second component is the first component squared minus 4. Well, hopefully you recognize from our previous examples that this relation has a graph. So it's super helpful if you can graph a relation, because it makes it a visual matter to see what the domain and range are. Because you can look at a graph and see what the first components are of the ordered pairs on the graph, and you can also see what the second components are, as long as you were able to graph it accurately. So in this particular case, this relation that we're looking at here is a parabola that points upward, and it's shifted down 4. So it'll look like okay, so there's a quick and dirty graph of the parabola P, and you can see some of the points I plotted on it. For example, 3, 5 is an element of P. Similarly, you've got 2, 0 there as an element of P, and so on. There's lots of points on that parabola. So then, what are the first components that can appear in that relation? Well, that's just the part of the graph that corresponds to the x-axis. Since the parabola opens forever to the left and to the right and every point in between, you can see just from the graph that the domain of P here is the set of all real numbers. If you want to use interval notation, you could say negative infinity to positive infinity, like so. How about the range? Well, the range are all of the second components that appear on the graph, all the y components of the points on the graph. So the range of P, well, you can see that the y values on this graph start at -4 and then go upward forever. So the range of P would be the interval -4 to infinity, or if you want to use set builder notation, it's the set of y's in R having the property that y is bigger than or equal to 4. And I just gleaned that from, knowing how to graph things and having some experience with this. And when you're looking at domain and range and sort of this sort of format, looking at a graph and understanding a numerical relation between the components, y equals x squared minus 4 in this case, this is the sort of thing that you've probably done in the past. All right, so for this next example, I want to change gears a little bit. I want to talk about, basically definitions and, where I've changed the names of the characters involved. So in this case, we've got T is the name of the relation, and it goes from X to Y. So instead of R and A and B, we have different characters. So I need to be able to, when I'm in a different context with different characters involved, I need to be able to write down what the definition of domain is. And I don't want to always have to flip back into the book and look up the definition. Rather, I want to think about my conceptual notion of what domain and range are to reconstruct what the, official definition is. So I know that domain is just the set of first components of ordered pairs in this relation. Now this relation T goes from X to Y, so that means that T is a subset of X cross Y. And so the domain, being the set of first components of this relation, must be those elements come from X. So the domain of T is going to be the set of all x's in X having the property that there exists some y in big Y such that x comma y is in the relation T. So what I captured here is that the domain of big T is the set of all first components. And if you think about it, that's what I've got here. I've got all the x's in big X that are paired up with some y as an ordered pair in T. And likewise, range is the set of all y, the second component. So it would be the set of all y's in big Y, and then there would have to exist some first component in the first set, big X, that pairs up with that. So such that x comma y is in T. So again, I just went with my conceptual notion that, hey, I'm trying to get all the second components of the ordered pairs that are in the relation. And that's what you come up with. So now it's plain to see at this point that the domain of T, since this is a relation from X to Y, the domain always lies in the first set. So that's important to remember. So the domain of T is in the first set X, and the range of T, being second components, is in the second set Y. It's a subset of it. Let's say you're in the middle of a proof, and you've got some character Q that you happen to know is in the domain of T. Well, what does that mean? If Q is in the domain of T, what does that imply? Well, the definition of domain would require that there must exist some point in the second set. Doesn't really matter what you call it. I'm going to call it Y. There exists some Y in big Y such that the element Q that's in the domain gets paired up with that Y, and that ordered pair is in the relation T. You have to do this sort of thing quite a lot when you're proving things about relations and later functions. Likewise, if you would have some element R is in the range, that means that R is paired up with something in the first set to get an ordered pair in the relation. So this means that there would exist some element in the first set, let me call that X, so little x is in big X, such that then that little x is paired up with that R, and that ordered pair is in that relation T. So what we're doing right here is really useful skills for doing proofs. Okay, the next concept is pretty straightforward, the idea of an inverse relation. Now, it may be that your hackles get up a little bit when you see the word inverse. You may remember, oh man, when I took calculus class, there were like these inverse, like trigonometric functions, arcsine and arctangent, and there were things like logarithms that were inverses of exponential functions, and those things are all really scary. So inverses must be really hard. Well, it's true that inverse functions can be a little bit strange algebraically, but when we're talking about relations conceptually, it's very simple. If you have a relation R from A to B, then the inverse relation of R, which we use that R, looks like raised to the negative first power, but we would just say that's R inverse. It's all it is you take all the ordered pairs that were in R and reverse the components. So R inverse is the set of all B comma A's, where A comma B is in R. So if you take every A comma B that's in R and just reverse the ordered pairs, that's how you form the inverse relation. In this example down here, I've got a relation R going from A, which is the set containing 1, 2, and 3, to B, which is the set containing A, B, and C. And the elements of my relation are listed there, 1 comma A, 2 comma A, and 3 comma C. If I wanted to say what the inverse relation is, it's really simple. R inverse, in yellow here, is the set containing A comma 1, A comma 2, and C comma 3. Easy peasy, right? And if I want to draw bubble diagrams of what's going on here, on the left I have the relation R, and so I could draw a bubble diagram for that by putting 1, 2, and 3 in the left set, A, B, and C in the right set. And I can draw some arrows to indicate the ordered pairs in the original relation R. So 1 comma A, 2 comma A, 3 comma C. In the right bubble diagram, notice that for R inverse, I've got the arrow pointed in the reverse direction. So I'm going to label the left set still is going to be A, and the right set is still going to be B. I just want you to notice that the arrow is pointing in the opposite direction. We could have put B on the left and A on the right if we wanted the arrows to point the same direction. Doesn't really matter though, as long as things are paired up in the right order. So all that's going to happen basically is that you reverse all the arrows so they point the opposite direction. So A comma 1 A comma 2, C comma 3. So notice that all you did was reverse the arrows of the picture on the left. So conceptually, an inverse relation is very simple. Just do the old switcheroo on every ordered pair in the original relation, and you get the inverse relation. So that's nice. So one fact that presents itself and is kind of obvious from the way that inverses are defined is that if you got a relation from A to B, the inverse, because it interchanges all the components of the ordered pairs, it interchanges domain and range. So what was the domain of your original relation becomes the range of the inverse relation. And what was the range of the original relation becomes the domain of the inverse relation. And so that's the content of fact 3.10 here. The domain of R inverse is the range of the original, and the range of R inverse is the domain of the original. So let's prove at least part of this. Maybe we'll prove this first part here. Domain of R inverse equals the range of R, and then I'll leave the other part of it as an exercise for you. So we'll prove just that domain of R inverse equals the range of R. Okay, now what I want you to think about in proving this is, on the most fundamental level, what kinds of things are we trying to prove are equal here? Well, we're talking about set equality here, right? Because everything is a set these days. And we know how to prove two sets are equal. We can do a double containment argument is one way to go about it. We can also play around with the set builder based definitions and then do some games with logic. And we could do that. We could do this one either way here, but just for the practice of it, I want to do a double containment argument. So I'm going to prove forward and reverse containments here. So for the forward containment, I would say, okay. Now let's think about things with sometimes good choice of variables makes your proof less susceptible to getting mixed up and less prone to error. So just real quick, over here on the side somewhere, with this bubble diagram up here, the original relation R goes from A to B. We know that the inverse relation goes from B to A. So if I'm going to take something in the domain of R inverse, well, since R inverse starts at B and goes to A, that means that the domain of R inverse lies over here inside of B, right? So maybe it would make sense to say let little b be an element of the domain of R inverse. Calling that element little b reminds me that it's in the set big B. And then I know eventually I want to, at the end, argue that B is in the range of R. Okay, that's my target. What does it mean to say B is in the domain of R inverse? Well, forget that it's R inverse for a second. What does it mean to be in the domain of any relation? To be in the domain of a relation means that you're the first component of an ordered pair that's in that relation. So by definition of domain, there must exist some A in big A that gets paired up with B in the relation R inverse, and B is the first component because it's in the domain. So there exists an A and little a and big A such that the ordered pair little b comma little a is in R inverse. Now, if little b comma little a is in R inverse, if we switch the components, we get an ordered pair that's in the original relation. So we could say by definition of inverse, a comma b is in the original relation. Let me go ahead and erase our target here. So now check it out. Just knowing this information, I can see that B, that element that we started with at the beginning, is the second component of an ordered pair that's in R. Well, that's exactly what it means to be in the range of the relation. So I can say because there exists a little a and big A such that the ordered pair little a comma little b is in R, we have B is in the range of R by definition of range. And now notice that we started with B in the left-hand set, and we just arrived at B was in the right-hand set. So that proved that containment. And then the reverse containment is going to go very similarly. I'd say it's a reverse the logic sort of situation. Okay, so to do the reverse containment, we would start with, let's say, little b in the range of R. Now again, it makes sense to call this element little b, because if I look at the picture on the top right here, we can see that the range of R, those second components, lie in big B. So if I take something in the range of R, it makes sense to call it little b to remind me that it's in the bigger set, big B. So apply the definition of range. So by definition of range, there exists some little a and big A such that the ordered pair A comma B is in R. And now when you get to talking about the inverse, thus the ordered pair B comma A is in R inverse by definition of inverse. And now we see that B is the first component of an ordered pair in R inverse. And anytime an element is a first component of an ordered pair in a relation, it's in the domain of that relation. So we have that there exists some A and big A such that B comma A is in R inverse. So little b is in the domain of R inverse, being a first component in that relation. And here we're using definition of domain. And again, we see that if you look at where we started with little b in the range of R, and we arrived at little b in the domain of R inverse. So we've proven that reverse containment. And then that's the proof. So the real skill that's going into this proof is that I know how to express what I mean by saying little b is in the domain of a relation, or little b is in the range of a relation. I have that definition sort of deciphered deep down in my heart so that like I understand it, oh, something's in the domain means it's a first component. But then I can translate that into there exists a little a and big A such that the ordered pair B comma A is in R inverse, that sort of thing. That's the real skill. And that's where people tend to have trouble with doing these kinds of proofs, actually. It's just making the leap, of using the definition appropriately. Next up is the concept of images and preimages. These concepts are very similar, actually, to domain and range. Images are a subset of the range, and preimages are a subset of the domain. And their definitions are very similar to the definitions that you have for domain and range, but just restricted a little. So let's start with image. So the setup is again, we have a relation R that goes from A to B, but this time we have a subset of A that we're calling S. I've depicted that over here on the left bubble. So you have the set A and then some subset S inside there. So then the image of S, which we denote by R of S because R is the relation in question here, is this set. And the interpretation of this set is it's the set of second components that live in big B that are paired up with some element that's in big S. So when I think about this image, it's the second components ordered pairs in R whose first components are in the set S. When I think of the concept of image, this is my sort of human interpretation of it that I carry around. And then what I can do is convert this sort of human version of it into this more technical version up here as needed when I'm doing a proof. But really, the part in orange is what I really carry around with me, and then I can reconstruct the other part as needed. Let's see how it works with a toy example. So in this first toy example here, I have A is the set of integers 1 through 5, and B is the set of Greek characters alpha through epsilon. And then we have a relation that pairs up elements in A and B. So R here is just some relation, a subset of A cross B. Notice all the first components are coming out of big A because they're just numbers. And the second components are all coming out of the set B because they're all Greek characters. Okay, so we have a relation, we have a setup. Now the additional bit is we have a subset of A. So our subset is 2, 3, and 4 that lives inside of A there, right? I want to find R of S. Okay, so all R of S is, it's the second components of ordered pairs having the property that the first component that they're paired up with is in S. So R of S, okay, let's just go down the line. Let's look at all the second components that are in R and think about whether they're paired up with something in S. Look at the first ordered pair. There's delta is the second component. Is that second component paired up with something in S? Well, no. Delta's paired up with 1, and 1's not in the set S, which is 2, 3, and 4, right? So I would not have delta in the image at this point. Maybe later I'll determine that delta is in the image, but not basis of that first ordered pair. Now let's move to the second ordered pair. The second component of that ordered pair is epsilon, and it's paired up with 2. Is 2 in S? Yes, it is. Well, that tells you that epsilon is in the image of S. So I would have epsilon here is in the image of S. Now let's go to that third ordered pair. Well, I've got epsilon again. Well, I already knew epsilon was in the image, but I see here epsilon's paired with 3, and 3 is also in S. So this is just a second reason why epsilon is in the image of S, but I don't need to write down epsilon twice because the image is a set and you don't need to write duplicate elements. Okay, when we go to the fourth ordered pair, we've got a second component of alpha there and it's paired with 3, and we see that 3 is in fact in S, so that tells me that alpha is in the image. And then in that last ordered pair, you've got beta is the second component and it's paired with 5, but 5 is not in S, so I would not include beta in the image of S. So that's it, we're done. Maybe I can squeeze in a little bubble diagram over here to sort of illustrate what happened there. Here's A, here's B, you got your relation R going that way. 1, 2, 3, 4, 5 in A, alpha, beta, gamma, delta, epsilon in big B. And I'm going to draw those arrows. And then the set S was 2, 3, and 4. So I'm going to draw a circle around 2, 3, and 4 here inside of A. So when you restrict your attention to 2, 3, and 4, where did the arrows point to? Well, if you follow the arrows emanating out of 2, 3, and 4, you see that they land on only epsilon and alpha, right? 2 pointed toward epsilon, 3 pointed toward epsilon and alpha. 4 didn't point at anything, so I didn't get any information from 4. So follow all the arrows out of that bubble, you get the image. You can see why it's called an image. It's almost like if you think of R as being some sort of projection from A onto B, then the shadow of the orange circle is what you get for the image. So now let's see if we can think about it in a less of a toy example with this parabola here. So this is that same parabola that we did before. We know what this parabola P in green here is a relation on R. And now the set that I'm going to look at S, that's a subset of the first sort of my domain, is the interval from -2 to 3. Since I'm thinking about S as being a subset of, sort of the domain bubble, the A set, if you will, that'll be on the x-axis of this picture. So think about S as being like here on the x-axis. And then you just ask yourself, what are the y components that are paired up with those x coordinates on that piece of the x-axis called S? Let me highlight that. So think about the y components that are paired up with S there. S is highlighted on the x-axis. The y components that I see paired up with that part of the x-axis looks like this to me. I'm going to highlight it in blue on the y-axis. That part of the x-axis corresponds to this much of the parabola that I'm highlighting in blue here, and it stops right there. So the y coordinates that correspond to that, I'll put on the y-axis here in green, like so. So what I have over here on the y-axis is your R of S. Those are the second components that are paired up with first components that lie in S. So R of S here is the interval from -4 up to 5. And the endpoints are included because the endpoints were included in S. If you want, you can call that the set of all y's in R, having the property that y falls between 4 and 5 inclusive, like so. Okay, so that's image. So essentially, with image, someone is specifying what some first components are, and you have to tell me what are the second components that get paired up with those specified first components. Now, when we do preimage, it's exactly the reverse of that. I'm going to specify what the second components are, and then you have to tell me what the first components are that went with those specified second components. The first components that correspond to those specified second components is called the preimage of that set of specified second components. The setup is the same. We have a relation from A to B, but this time we have T, a set T that's a subset of the second set B. So we're starting with second components, because that's what the set B is, right? The set B is sort of where the second components of the relation live. So we're starting with some second components called T, and then the preimage of T are just those first components in A that get paired up with those elements that are in T. So just like before, I'm going to write this like kind of what my human version of it is. So the human version of this is the set of first components paired with elements in T. So up here, image was a set of second components whose first components were in S, and preimage is a set of first components that are paired. Maybe if I want to word it the same way as I worded it the other way, I would say something like so this would be the set of first components paired with second components from the set T. Okay, so now in the toy example that I have here, it's the same relation as we were playing with before when we were dealing with image, but now we're going to do preimage. So we have this relation that pairs up numbers with Greek characters, and then we have a set big T that lies in the set big B up here, and we want to know what first components get paired up with these elements in T. So preimage of T is just, okay, is there anything, like what's paired up with alpha? Just ask yourself, what's paired up with alpha in this relation? Well, as I look into the relation, I see that 3 is paired with alpha. So 3 would be in the preimage of T. Is there anything else paired up with alpha? No, I don't see anything. How about beta? What's paired up with beta? I see that 5 is paired up with beta. I don't see anything else paired with beta. Then I can go to gamma. What's paired with gamma? I don't see that anything's paired with gamma. So then I'm done. The preimage of T is 3 and 5. So just like that. Someone handed me the second components, and I had to give the first components that went with those second components. And the same thing can happen when you're given a graph, like on a parabola here. So on this parabola, someone's giving me some y values on the graph, and I got to say what x components are paired with them. So the y components that I'm being given here are between -6 and 0. So let me indicate those on the axis here in blue. So -6 to 0, like, so my set T kind of looks like this, kind of shaded in blue there. So here's the set T. Those are y components. Now, what are the first components that get paired with y components from that set? Well, I can see that the part of the graph that corresponds to that piece of the y-axis goes, I'm going to highlight it in yellow here on the parabola, like there to there. It's just that sort of part of the parabola that lives below the x-axis. And then I read off the part of the x-axis that corresponds to that part of the graph, and it would be from -2 to 2. So the preimage of t, so those first components that go with things in t is the interval from -2 to +2, like so. So conceptually, it really wasn't any different than the toy example above, but it was just, a little bit more work to have to look at the graph and glean what the first components were given the second components. All right, so here is a good chance to practice these skills just with a toy example. So just a straightforward example I want you to do. So the setup here is we have this two sets. A is the integers 1 through 5. B are the Greek characters, alpha through epsilon. And I have this specific relation from A to B. And then I'm asking you to find domain and range, inverse, some domain and range of the inverse, and then some images and preimages here on the last four. So take a few, press pause, take a few minutes, and see what you can do with this one, and then we'll work through it together when you come back. Okay, so let's go through this quickly. For that relation, R, the domain is just all of the first components that appear as ordered pairs in that relation. So the domain, I'm just going to list off the first components that I see, and I see 1, 2, 3, and 4. The range of R is just the set of all second components that appear, and I see beta, gamma, and epsilon. I'm not going to list beta twice because we don't need to list duplicates. What is R inverse? R inverse means take all the ordered pairs that were in R and just reverse their order, and you get the inverse. So for R inverse, I would get ordered pair beta 1, ordered pair beta 2, ordered pair gamma 3, and ordered pair epsilon 4. The domain of R inverse, now that I have R inverse just sitting there staring at me, I can just read off what its domain is. The domain of R inverse is the set of all first components that appear in that relation. Alternatively, I could remember the theorem that says that the domain of R inverse is the same as the range of R, which I've already listed, is beta, gamma, epsilon. Notice, however, I would have gotten that if I would have just listed off the first components that appeared in R inverse right here, right? So either way, the range of R inverse, we had the fact that told us that the range of R inverse is the same as the domain of R, and we already listed the domain of R is 1, 2, 3, 4. Or alternatively, we could have listed off all the second components that appear as ordered pairs in R inverse, and we would have gotten the same answer, 1, 2, 3, 4. Okay, the image, this R of the set 1, 3, 5 is the image of that set. The image of the set are the second components that get paired up with those elements. So I just have to list all the things that are paired with 1, all the things that are paired with 3, and all the things that are paired with 5, and I'm going to eliminate any redundancies that might happen if I do that. So what gets paired with 1 in the original relation? Well, I see that beta gets paired up with 1, and 3 gets paired up with gamma, and that's it. 5 is not even a first component, so I don't get anything from the 5. How about what is R of the singleton 5? Well, I look into the original relation and I ask myself, what's paired with 5? The answer is nothing. Nothing is paired with 5. And what's my set theoretical way of saying nothing? Well, that's your friend, the empty set. So R of the singleton 5 is the empty set. Okay, what is the preimage of beta gamma, the set containing beta and gamma? Well, I just asked myself, what are the first components in the original relation that get paired with beta and or gamma? So what's a first component paired with beta? Well, I see that beta actually is paired with 1 and 2, right? Beta got paired with 1. 1 and 2 are first components of beta in that original relation. Right up here, right? This ordered pair and this ordered pair. The first component is, or the second component is beta, so we see beta is paired with 1 and 2. And then gamma gets paired with 3, and that's it. So, and then the preimage of alpha delta. So what's getting paired with alpha? What first component gets paired with alpha as a second component? Well, I don't see alpha appearing as a second component anywhere, so I don't get anything from alpha. And also, I don't see delta is paired with anything. So the preimage of alpha delta is nothing, the empty set. Nothing gets paired with alpha or delta in that original relation. All right. Okay, so this is another example I want to drill you on a little bit, is dealing with things like the domain, the range, image, and preimage in the abstract. So I want to have some different characters now. So this time I'm going to have K as a relation from a set M to a set N. And I'm going to have a subset D of M and a subset E of N. In my bubble so I've put a blank bubble diagram over here because, like I told you, I'm a very visual person. So since this relation is K, the arrow up the top will name K, the left set will be M and the left set will be N. And then we have D is a subset of M. So here's the set D inside of M. And we've got a set E that's inside of N. Okay, so then I want to just say, according to the definition, what does it mean to say S is in the domain of K? Well, this is one we've done before, but it doesn't hurt to practice this a few times. To say something's in the domain simply means that it's the first component of an ordered pair that appears in K. So S is the first component. So if it's a first component, that means there has to exist a second component that goes with it, right? So this means that there must exist some, and I might as well call it little n, inside of big N. So that's going to be my second component that gets paired with S. So such that S comma N is in the relation whose name is K. Now, what does it mean to say S is in the preimage of E under K? So this, S is in the preimage of E. Well, when something's in the preimage, it's a first component, and the thing that it's paired up with as the second component lives in E. This means there exists some E in big E such that S comma little e is in K. See how domain and preimage are very similar? Preimage is like domain where you've specified what the range values have to be. Now let's do range and image. So we've got T is in the range of K. All that means to say something's in the range just means it's a second component of some ordered pair. Well, if T is a second component, there must exist some first component. Might as well call that little m, and it lies in big M, such that M comma T is in K. Next, let's talk about what it means to say little t is in the image of D. So this T is in K of D. So again, this means T is a second component, but it means that the thing that T is paired up with as a second component comes from the set D. So this means there exists some, let's call it little d in big D, such that D comma T is in K. So again, notice how range and image are very similar. Range is sort of like all the possible second components, whereas the image are just those special second components that get paired up with things in the specified set in the domain. Being able to do this sort of thing, though, like we've done in these 4 bullet points here, super important when you're doing proofs. Like if you're going to prove something about range, and it's going to be some sort of set argument where you're maybe going to do an element chasing argument, you know, you always start when you do an element chasing argument by taking an element in one set, and then you argue that that element's in some other set, right? So you have to be able to say what it means that that element T is in that set. You have to be able to write down exactly what that means. So this is a very important skill to have here. let's put some of that skills to some of those type of skills to the test, being able to say what it means for something to be in domain and range, and take a look at this fact 3.15. Maybe we'll prove some of it. So in this setup, we have two relations. Now both of these relations are relations from the set A to the set B. So the idea here is R1 and R2 are both subsets of A cross B, right? Being relations from A to B. And since both R1 and R2 live in the same set, it would make some sense. You could think of A cross B as being the universal set. So you could talk about unioning R1 and R2, or you could talk about intersecting R1 and R2. You could take set differences. You could do complements. There's all sorts of things you can do. In this theorem, we're just going to look at unions and intersections and think about how do the operations of union and intersection interact with the concepts of domain and range? And that's what this fact captures over here. If you want to get the domain of R1 union R2, it's exactly equal to the union of the individual domains. And also, same for range. If you want to do the range of R1 unioned with R2, so first you would union R1 and R2 and then take the range, it's the same as taking the individual ranges and then unioning them together separately. And notice we get equality here on both of these. However, in 3 and 4, when we switch to intersection, we don't necessarily get equality. If you first intersect the two relations and then take the domain, all you can say is that that result is a subset of the intersection of the individual domains. And similarly for range. So anyway, what I think I'll do here is prove part 1, and the other ones are pretty similar, and I'll leave those as exercises. Maybe those will appear as homework exercises. So let's do part 1 here. So part 1, I'm trying to prove that the domain of R1 union R2 is equal to the domain of R1 union separately with domain of R2. Now notice again, what are we proving? What are we trying to prove is equal here? What kind of objects are we proving are equal? Well, that would be set equality. And we know how to prove set equality. We can use double containment arguments. And that's what I'm going to do here. So I'll prove the forward containment by taking an arbitrary element in the left-hand set. So, okay, now again, I've got two different relations, but they're both going from A to B, right? And so if I start talking about domain of R1 and domain of R2, those are elements of A, the set big A, because we're talking about first components of these relations, and both of these relations have their first components in the set A. So it'll make sense for me to let my arbitrary element be little a. So let's let little a be in the domain of R1 union R2. Okay, here's where I have to do that skill of saying what it means to say an element little a is in the domain of a relation. To be in the domain of a relation means that you're the first component of an ordered pair in that relation. And if you're a first component, there has to be a second component. There exists a second component that goes with it. So then by definition of range, there exists some b in big B such that the ordered pair a comma b is in R1 union R2. I'll erase those bubbles there to get in my way. Okay, so the next thing we could do is consider what it means for that ordered pair to be in that union. So a comma b in that union tells us that a comma b is in the first one, the first relation, or it could be in the second one. It could be in both, but all I know is that it's in one or the other. So we can consider those two possibilities in turn. If it's the case that a comma b is in R1, well then little a appears as the first component of an ordered pair in R1. That means little a is in the domain of R1. And notice that the domain of R1 is certainly contained in the domain of R1 with some other set. So if I union domain of R2, it's still true that a would be an element of that union. And if little a comma b is in R2, we have a similar sort of thing. then little a is in the domain of R2 in that case, because A is a first component of an ordered pair that appears in R2, but that domain of R2 is certainly in the union of domain of R2 with some other set. So it would be in the domain of R1 union domain of R2. So either way, we have A is in that union, right? And at this point, if we think about what we've established, we started with A in the left-hand set, and we just arrived at A was in the right-hand set. So that proves that containment, and then we'll do the reverse containment. And we'll do that by letting little a be in the domain of R1 union domain of R2. And sort of reversing logic here, we can say A has to be in the domain of R1, or A is in the domain of R2, and we'll consider those two possibilities separately. If A is in the domain of R1, then there would exist some B in big B such that, I'm going to call that B1, okay? There exists some B1 in big B such that little a comma B1 is an element of R1. But notice that R1 is certainly contained in the union of R1 with some other set, right? If I union R1 with some other set, I'm just going to get something potentially larger. And thus, a comma B1 is an element of R1 union R2. And so now we see that little a is the first component of an ordered pair that lies in the union R1 R2. So this tells me that A is in the domain of R1 union R2. Also, if A is in the domain of R2, same sort of argument's going to work here. Then there would exist some, I don't know it's the same B as before, but there would exist some B2, let's say, in big B, such that A comma B2 is in R2, but that's certainly contained in R1 union R2, and we arrive at the same conclusion. Thus, A comma B2 is in R1 union R2, so A is in the domain of R1 union R2. Either way, considering the two possibilities, we have A is in the domain of R1 union R2. And then when we think about what we were out to prove originally, well, we started with A in the union of those separate domains, and we arrived at A had to be in the domain of the union of those two relations. And so we've proven the reverse containment, and having proven both containments, we've got equality, so we're done. All right, so I think I'm going to stop talking there about relations in this first video. So what did we talk about today? Let's recap. So we presented the notion of what a relation is, and a relation really doesn't have that much structure. All a relation is a subset of a cross product. So if you look at the cross product A cross B, any subset of that is a relation from A to B. So that doesn't carry with it that much structure, but it does carry order. There's always a first element and a second element in that ordered pair. We also introduced the idea of an inverse relation, and an inverse relation also doesn't carry with it that much structure, because all you do to get an inverse relation is to take the original relation and reverse all the ordered pairs. But we'll see later when we start talking about functions that that's still a pretty powerful thing to be able to do. It really helps us advance our proofs a little later when we realize that we're just reversing components of ordered pairs. So it'll be useful to remember. And then we introduce some more technical definitions related to relations. We talked about the idea of domain and range. So what's really going to be important as we move along in this class is, in proof writing, you need to be able to say what it means when A is an element of the domain of R. You have to be able to interpret what that means in terms of ordered pairs. Same thing for if you say B is in the range. You have to be able to write out what that means. And also, we talked about images and preimages, which are sort of similar ideas to domain and range. And again, the idea that I want to impress upon you about those definitions is being able to work with them on that elemental level. Whenever I say X is an element of the preimage of some set, you need to be able to tell me about X. How is X related to ordered pairs in those sets in question? So it's really going to be important to advance your proofs to be able to say exactly what it means, and elements in the domain and elements in the range. Super important. And we'll be proving a lot of things about domains and ranges and images and preimages when we get to the chapter on functions. Next up, we're going to talk about relations of a special kind called equivalence relations. And a little later in this same chapter, we'll talk about special kinds of relations that are called orderings. So relations really have the flexibility to capture, when you layer on a few special properties, things like equivalence. So equivalence relations is sort of capturing the idea of when things are the same but not identically, like equal. Like, for example, two triangles in the plane can be congruent, but that doesn't mean they're literally the same triangle. This triangle's over here and this triangle's over here. They're not the same triangle. But if all you care about is the geometric properties of the triangle, when you say those triangles are congruent, then they're the same for all you care if all you're interested in are geometric properties. This comes up a lot in math. Things like in abstract algebra, we have the idea that certain kinds of algebraic structures are the same for all we care, and all we care about is the algebraic properties. So it's a pretty prevalent idea in modern mathematics. And then we'll talk about ordering. So these are things like less than. And it'll turn out that examples like divides serves as an example of an ordering. So and orderings are pretty important in the foundations of mathematics as well. So we have a lot of stuff based on relations, and so it's a really cool playground for us. So I'll stop there, and we'll talk again soon. Bye now.